Kia ora Year 12 and 13. This is question 4 from Scholarship Calculus 2015. So this is an optional question. You are allowed to choose between the either option, which we've already looked at in class, or this option. So this is a linear programming problem, and when you first start looking at scholarship papers, you might freak out that we haven't done this achievement standard. So it's actually probably the easiest question in the whole paper. What you need to do is make sure you've read through the question very, very carefully, and probably that you've got the words in front of you so you're not going through the rest. I want you to have a go now at writing whatever mathematical statements down you can about the situation, because the first thing we're asked to do here is to write down the inequalities, the 5 constraints, in addition to this, this and this. So that's part 1. Okay, so this is all about a cake factory, and it makes cake decorations. So it's got 3 different kinds of packs. They are red, white and blue. I will do 3 colours of pen. So red, white and blue. And each pack has got 3 different types of decorations. So type A, type B and type C. Now if you've done the 3.15 standard, which is simultaneous equations, it should be starting to feel a little bit like that already. Each red pack has got 6 type A decorations, 3 type B and 2 type C. The white packs have a different combination, and the blue packs have a different combination again. So 2, 4 of B and 4 of C for the white pack, and so on. Right, now this question even defines your variables for you, which kind of surprised me, and it tells us that the factory makes X red, Y white and Z blue packs every hour. Now, if that hadn't happened, that would have been the first thing I told you to do, is to let something be X, something be Y and something be Z. Then we're told that the maximum number of each type of decoration available is 500 of A, 400 of B, and 300 of C every hour. The factory has to pack at least 1,000 decorations every hour. So just notice that decorations and packs are not the same thing. We also get told that it has to pack more type B decorations than type A decorations every hour. So the first few points of this question are just to turn that word situation into some little inequality. I'm going to start doing that on the next slide. Right, well, we've got 3 things that we don't really know about yet. So let's write those down. Right, the first one is the type A decorations. Right, and if you've done simultaneous equations with me, you'll remember that I always said to just label your equations and then work out what we've got. So where do the type A decorations get used? Well, every time they make an X pack, they have to have 6 type A decorations. So it's going to be 6x, and every time they make a Y pack, so Y pack is a white one, they use 2 type A decorations, and every time they do a blue pack, they also use 2 type A decorations. So we've got 6x plus 2y plus 2z, and we want to have that, when we do simultaneous equations, we have an equal sign, but here we know that the maximum number of the type A decorations they can do is 500. Right, so that's got to be less than or equal to 500. Right, we do the same thing for the type B. Right, so where do the type B decorations get used? Well, every red pack has got 3 of them. So there are 3 for every X pack. Every white pack has got 4 of them, so that's going to be 4. And how many do we use in the blue pack? We use 5. So it's going to be 3x plus 4y plus 5z. And the maximum number of each of the type Bs is 400. So there we go. Right, so if you've done simultaneous equations, this will feel easy, but if you haven't, you're probably going to need to go through this a couple of times. Once you get it, it's, as usual, that's fine. So type C decorations get used in the red pack, the white pack and the blue pack. There are 2 type C decorations in every red pack. Okay, and then just reading through it, there are 4 in every white pack and there are 2 in every blue pack. And altogether, the maximum number of type C decorations is 300. Alright, so that's the first step towards answering the question, you can see straight away that we've written 3 inequalities. Now, notice that you're told to simplify your answers. I'm going to come back to that at the end. So what else do we know? Let's keep reading through the question. What's next? Well, we're told something about every hour they must pack at least 1,000 decorations. So let's think about what they pack per hour. Well, they have the X packs, the Y packs, and the Z packs. So every hour, how many type A decorations do they pack? Well, it's whatever they put into each of the types. So we're going to add these up. So it's going to be 11X plus 10Y plus 9Z. That has to be more than at least 1,000. Right, so the factory must pack at least 1,000 decorations every hour. Okay, so I'm going to go over that one more time. Every hour they pack X number of red packs, Y number of white packs, and Z number of blue packs. Okay, so altogether, the decorations that they pack are the combination of all of those. So that's why I'm adding up these 3 to get that bottom one, right? And they must altogether be packing 1,000 decorations an hour. So that's going to be my 4th inequality. Now, the last thing we're told is that they must pack more of type B than type A every hour. So this is how many type B decorations they pack per hour. Oh, whoops, and I want type A, so not that one. Ugh. Okay, forget that I did that. Let's see if we can get rid of that. Yep, so we're going to now compare these two. I'm going to do that on a new slide. And then I'm going to start numbering and simplifying. Alright, so we want to say that they have more B decorations. So which way around is it? Let's see. More type B decorations than type A decorations. So 3x plus 4y plus 5z, that's my B decorations, has to be greater than the A decorations, which is 6x plus 2y plus 2z. So we can simplify some of these now. Okay, the first one I'm going to do, so that's our 5, it's used up all the information about inequalities in there. And the question even tells you that you need to have 5 constraints. Okay, so that first one was our type A decoration. We started writing it as 6x plus 2y plus 2z is less than or equal to 500. We're going to simplify that now, and that's simplifying here really is simple. We're just going to divide everything through by 2. So we get 3x plus y plus z is less than or equal to 250, right? I reckon that has to be the easiest mark in the whole scholarship paper. There we go, that's the first constraint. The second one, which I'm going to label 2, funnily enough, is how many type B decorations have I got? Well, it's 3x plus 4y plus 5z is less than or equal to 400. Is there any simplifying I can do? No, there's no common factors. Sorry, there are no common factors. So that's 2 of the inequalities that we've done. So on to the next 3. Right, now the third inequality is the type C decorations. So it's 2x plus 4y plus 2z is less than or equal to 300. Again, I'm just going to divide through by the common factor and end up with x plus 2y plus z is less than or equal to 150. There we go. Now, the next one we already had, 11x plus 10y plus 9z is greater than or equal to 1,000. So this is the constraint that the total amount they have to pack must be 1,000 or more. Right, so that's number 4. Can't simplify that, so we're fine. Finally, I've got the funny one about more B decorations than A decorations being done. So we had that as, I can't remember which way around I did it, so 3x plus 4y plus 5z was the B decorations. And that's got to be greater than 6x plus 2y plus 2z. So we're going to simplify that by just collecting up like terms. So be careful doing this. We're just going to subtract a whole lot of stuff. And we will get, let's take everything over to this side to start with. No, I'm not going to do it that way. So we'll go the other way. 0 is greater than 3x minus 2y minus 3z. Right, but we're going to rewrite that. Am I going to rewrite that? No, I'm just going to leave it like that. So there are my 5 inequalities. So that is, I think, probably 5 out of 8 marks. Alright, so the big message here is do not ignore the linear programming question just because we haven't done those credits. Credits have got absolutely nothing to do with scholarship, which is a very good thing. Right, so the second part of the question is not even to solve what the factory should do, it's just to answer this question. Given that every hour the factory produces 100 packs in total, identify the feasible region on the diagram that they give you. So we'll take a look at the diagram now. Okay, so this diagram is so loaded with clues of what to do, once you know where to look, that it's kind of crazy. You can see that we have a two-dimensional graph. We've got x and y. So obviously somehow we've got rid of z. So how did we do that? We did that because we were told that the factory produces 100 packs in total every hour. So that means x plus y plus z is equal to 100, just as we did back in probably year 12 or year 11. We can eliminate z. So z is equal to the leftover, 100 minus x minus y. So what we're going to do, we're going to go back through our 5 constraints, and we are just going to rewrite z as this. Okay, but the scholarship paper even gave you these lines here. Right, so it turns out that when you do stuff with your 5 constraints, you're going to end up with those lines, and then you're going to do some beautiful shading out, so that what we get left with is what we call the feasible region. Okay, so I'm going to talk more about this in one of the tutorials, hopefully very soon. But the feasible region is basically which x and y combinations will satisfy all of our constraints, all of our inequalities, and this equality here as well. The reason that I shade out is because it makes it easier to see the leftover bit, which is the feasible region. Okay, so it doesn't matter if you shade in or out as long as your answer is clear, but I find shading out easier. Okay, so let's take a look at each of these things. So our first one, we had 3x plus y plus z is less than or equal to 250. So we quickly substitute in this. Z is equal to 100 minus x minus y. We get 3x plus y plus 100 minus x minus y is less than or equal to 250. Right, so you can see the algebra we're doing here is just crazily simple, right? 2x, the y's have gone. What have we got? 2x plus 100 is less than or equal to 250. So hopping straight to this, we get x is less than or equal to 75. So if you look at that diagram in front of you, you can see that they have given us a vertical line at 75. So that's what that vertical line is on the picture, right? So they're not even asking you to draw the 5 inequalities once you've done Z. They've given them to you, and what they're looking for you to do is to shade. So what we're saying is we want to shade things that are not satisfying this. So we're going to shade the infeasible region and then point to the feasible region at the end. So we're going to shade everything on that side. Okay, so I'm going to put in, I'm not trying to work out how I do this with the iPad app so that it works. Okay, so here's my picture. So the first thing I can shade in is that everything out there is not in the feasible region. So not in FR. And I'm going to do that now for the other 4 inequalities. And I think I'm just going to duplicate this slide. Right, so now I'm going to move on to equation number 2, which is 3x plus 4y plus 5z is less than or equal to 400. Okay, now this video is getting really long, so I'm just going to hop straight to the end here, because I think everyone watching this can substitute properly. When I substitute in my constraint here, what I end up getting is a couple of lines of algebra, and then 2x plus y is greater than or equal to 100. So you might want to think about that as in y equals mx plus c form. We're going to get y is greater than or equal to negative 2x plus 100. So that's my feasible region. So I'm going to shade everything with the y values are less than that. So looking here, this equation here, oh sorry, this line here is that line. So now I want to be shading not y values greater, which is my feasible region, but I'm going to shade out. So there we go. Okay, that's that one there. Okay, next constraint, I do the same thing. The next constraint is looking at my type C decorations. So it's the one that starts off as x plus 2y plus z less than or equal to 150. So again, substitute in there for z, right, and manipulate that a little bit, and you end up with y is less than or equal to 50. Right, and we want to shade out, we're going to shade not the feasible region. The feasible region is y is less than or equal to 50, so we're going to shade higher than that, y is greater than 50. So that's what I'm going to shade up here. And you can see we're heading towards a feasible region, so you could just about guess at this point where it's going. The next one, you're going to substitute a z again. So from equation 4, you get to y is greater than or equal to negative 2x plus 100. Right, so that's the feasible region going to be y values. Now where's that one? So that is the same equation again. Okay, now that makes sense actually, but I'm not going to go into why, but it's the fourth equation is a linear combination of 1, 2 and 3, so it's not giving us any new information. So it's the same shading as before. And then the fifth equation is this one here. We end up with shading y is less than, so the feasible region is y is less than negative 6x plus 300. So we are going to shade the infeasible region, which is all the stuff up here. So that leaves me with a beautiful little feasible region, which is this little triangle in here. Right, so I know this has probably been the longest Schol calculus video I've ever done, but it's really the easiest question I've ever done. So if you want more detail on how I got into shading, what I'm talking about with the feasible region, either come and tell me or leave me a comment in the video if you're watching this from another. Alright, but linear programming is covered in the new Delta textbook, but not in the old one. But there are examples of it in previous years' papers as well.